Okay, let's start on section 5.3, an introduction to polynomials and polynomial functions. So I've just given right here two examples of polynomials. We've got a lot of definitions. The definitions are important because I will use them and you need to know what I'm talking about when I use them. So there are an infinite number of polynomials, and here is a polynomial in the variable x. Notice that it is a sum, and there's a constant term 1 that never changes. 3 times x, that's a variable term. That means its value depends upon the variable of the value of x. And 5x squared, again, x squared is a variable, and 5 times that variable, we can't know its value, so it's another variable term. So this is a polynomial in the variable x. Remember, x is a dummy variable. Depending on what we want to do, we might change the variable to t. If, for example, we want to consider changes over time, and we want our independent variable to be time rather than something else, it still is just a variable, and it still takes on real number values, or values in the domain. A polynomial in the variables y and x. Notice here, I want to show you something. This is a polynomial in the variables y and x, 5x plus 3y. Now, you've seen this type of a thing quite a bit, but here's what I want to tell you. When you say it's equal to 12, this is no longer a polynomial. Polynomials are mathematical expressions. And I'm just giving some quick examples right now before we give the full list of definitions. No longer, I need an R in there, a polynomial. It is a polynomial equation. So as soon as you put an equal sign in there, it becomes something a little bit more than just a polynomial. The term polynomial is still included in its describer, but the term equation is really important. So remember, these are the polynomials. Indeed, 12 is a polynomial. It's a polynomial with one term, and that one term is constant. So a polynomial equation, as you can see when we get to it later on, is a mathematical statement that states two polynomials are the same. So with that said, let's actually go down and start looking at some of our key terms and definitions. So a term is a non-zero number or the product of a non-zero number and one or more variables. So when we go and we look down here, this is a polynomial. This is one term, 5x squared. It's a product of a number and a non-zero variable. This is another term, the product of a number and a non-zero variable. And this is another term. It's a non-zero constant. Now let's break it down even more. The coefficient is the numerical component of a term. So 5 is the coefficient of the x squared term, and 3 is the coefficient of the x term. And sometimes we say 1 is its own coefficient, but usually we talk about coefficients when there's a variable term. A constant term is any term that is just a real number with no variables. So again, this is the constant term in this simple polynomial. A polynomial in the variables x, y. Literally, a polynomial can be have any number of variables. The number is usually restricted to be finite. It's a finite sum of terms. You can ignore, pretty much we're only going to be seeing in this class polynomials in one variable, although when we get to polynomial equations, you've already been dealing with them in two variables, but really no more complicated than that, except just to get down some of the basics. But as actually working with them, those are going to be the only case. And of course, it's a finite sum. How many terms do we have in this sum? Now remember, when I say 7 minus 5x, that's a polynomial. That's the same as 7 plus minus 5x. So all of these, even though there's a minus in there, we call it a sum. Sometimes people will say it's a sum or difference of terms. And if you want to think of it that way, a sum or difference of terms, that's fine too. Mathematicians can be really lazy with language, and it also has to do with our affinity toward logic, since every subtraction can be represented as addition, and what's being added is the the additive inverse of a number. We just say sum. But if you need to hear sum or difference, that's fine. It's a finite sum of terms. Here, finite just means it's not infinite. There's some number greater than that number. 1, 2, 3, finite. And we're always going to be dealing with probably no more than 3 or 4 terms. A polynomial whose terms contain only one variable is called a polynomial in the variable name. Just like I have right here, this is a polynomial in the variable x. Many times we suppress in the variable x when it's evident that the polynomial is just in that variable. Here are some more classifications of polynomials. So let me give you kind of a picture of this. So here we have the world of polynomials. It's a big, huge, gigantic world. You can say it's the set of all polynomials. Well, in that set of polynomials, we have 3 subsets of note. They don't overlap. And this classification, so once you have a set of things, you can classify them a lot of different ways. So this classification is a classification of the number of terms they have. So a monomial, just one term, for example 2x. A binomial, I should have wrote these bigger, binomial is 2 terms, like 5x squared plus 1. And for this last one, I'm going to write it down here. A trinomial is 3 terms, such as x squared minus 2x plus 1. So these are classifications by the number of terms they have. The degree of a term. So the degree of a term is the sum of all of the exponents of the variables given in the term, or 0 if it has no variables. So each one of the polynomials I have up here, each term just has one variable. So the degree of 5x2, well, the exponent, there's only one exponent and there's only one variable, and that's x. So this is a degree 2 term. This x, we don't write it down, but it has an unwritten exponent value of 1. So this is a degree 1 term. And if it doesn't have any variables at all, we say it's a degree 0 term. We learned that x to the 0th is equal to 1 as long as x is not itself 0. So we could say 1 is equal to 1 times x to the 0, and that's equal to 1 times 1. Or we could say 5 is equal to 5x to the 0, and that's just 5 times 1, which is 5. And there we can understand the reason we're assigning the degree of constant terms to be 0. We don't really literally want to do this, because remember, x to the 0th is equal to 1 only if x is not 0. And many times we want to substitute 0 in for the value of x. So this is just kind of, if you forget what a constant term is, just remember x to the 0th is equal to 1, and that's a constant. That might help. So let me give you another example. We have a whole bunch of examples. Let's just go down. So here's tons of examples. Let me make this a little bit bigger for you. So each one of these are terms. Notice our coefficients are real numbers. They don't have to be whole numbers. They don't have to be integers. They could be fractions. They could be decimals. 1.2x to the fifth. That's a degree 5 term. X cubed times y. That's a polynomial term in the variables x and y. It has degree. Let's see about this. This is a commonly missed question on the exam. So let's look at this particular example. X cubed times y. So first, it's a polynomial term in the variables x and y, and the degree is defined to be, let's go and review, the sum of all of the exponents of the variables. Well, y has an unwritten exponent of 1, so the degree is equal to 3 plus 1. So this has degree 4. This is a degree 4 term. Minus z, all of these are terms. Notice, another thing I want to show you, this one here, x to the 9th, was it divided by something? Let's say it was divided by 7. That is the same thing as 1/7 times x to the 9th. So your ability, we're assuming that you've got this down. I know by experience it's a bad assumption. X to the 9th divided by 7 is the same as 1/7 times x to the 9th. 10, to help you remember, 10 divided by 2 is the same as 1/2 times 10. So there's your paradigm example for remembering that rule. So the coefficients of these terms are 1.25, 1, minus 1, 2, 1/7, and 1/7. Oh, I actually tell you right there, show the equivalence. The constant terms, there's just one constant term, and it's 2. The polynomial in the variable x is x squared minus 10x plus 20. Just another example. The variables in this is just in the variable x, and here's a polynomial in the variables xy, 5x plus 3y. Each of the terms given in A taken by itself is an example of a monomial, because a monomial is just is a polynomial with one term. To form a binomial, take any two terms from A and add or subtract them. To form a trinomial, take any three terms from A and add or subtract them. The degree of a term is the sum of all the exponents. And here I explained to you what I did already. X third times y is equal to x to the third times y to the first is equal to 3 plus 1, which is 4. So the degree of 1.2, x to the fifth, there's only one variable, so it's 5. So let's actually play around with that. You should take note of this. It's a question that usually appears upon an exam, and for some reason it's missed quite often. So 2a, so 3x squared. So we just look at its single variable, and it only has one exponent, so let's do it this way. It has degree 2. So I'm going to make a little table with all of these. So it will be term and degree. That might help. And we have 1, 2, 3, 4, 5, and we have 5. Good enough. So our first term is 3x squared. The degree is 2 minus 2 cubed x to the fifth. So this is a good example. The degree is the exponent value, the sum of the exponent values on the variable. Minus 2 to the third is minus 8. So that's the coefficient. The variable is just the x term, so the degree is 5. Y? The degree is 1. 12x squared y z cubed. Well, the degree on the x term is 2. The degree on the y term is 1. And the degree on the z term is 3. So it has degree 6. And 5.27, it's just a constant term, so by definition it has degree 0. So the degree now of a polynomial. Notice that this is different. We were earlier we were talking about the degree of terms. This is the degree of an entire polynomial. And it's defined to be the degree of the largest of all of its terms. Or the, I guess better said, is the largest degree of all of its terms. So let's take a look at this. We'll do both of these. It's kind of already in a table there, so I'm going to be really lazy. It's Saturday. That's the reason I have on a NASA shirt. There's a launch tonight at actually just past midnight. And they're still really quite thrilling to me because I've only lived here actually just under 2 years in this area. So let's do these. So the degree of the polynomial, so let's just do the degree of each one of the terms. So 7x cubed has degree 3, minus 3/4 x has degree 1, and 2 has degree 0. So in this list, the largest of those numbers is 3, so it has degree 3. How many terms does it have? It has 3 terms. So that means it's a like tricycle, trinomial. Minus x, y, z. Well, it's only one term, so its degree is 1 plus 1 plus 1. So it also has degree 3. So it only has one term. So it is a monomial. X to the 4th minus 6.5. This is 2 terms. So it is a binomial, like bicycle. And the degree of the first term is 4. And the degree of the second term is 0. So the largest in that set is equal to 4. So we get 4. So find the degree of the polynomial here, given. So let's look at the degree of each term. The degree of the 3xy term is 1 plus 1. So that has degree 2. The degree of the x squared y squared term is the sum of the exponents. That's degree 4. Degree 2, degree 0. So we take the max of all of these numbers, and the maximum of all of those numbers is 4. So the degree of this polynomial is 4. So here we go with polynomial functions. So we're all ready to get into polynomial functions. So a polynomial function over the real numbers, that means the coefficients come from the real numbers, is a rule that given a real number as input determines an output based on that real number, where every input has just one output. So a polynomial function in the variable x is simply a function where the rule for the input value x is given by a polynomial. Such functions are denoted by expressions like f of x, g of x, h of x, p of x, and so forth. And that reminds me of something I want to talk about. Is it in this original list? Okay, so it's not. So I need to add something that did not get written down. So addition. Added qualification. I'll actually add it to my list and re-upload the notes. I usually try to write the notes from what it says pretty much in the textbook. All exponents are in the set 1, 2, 3. In other words, 5x to the minus 1 is not a polynomial. Remember the x to the 0th? That's just to help you to remember that the constant term has degree 0. We really don't put an x to the 0th in there, except on occasions when we're doing polynomial division to help as a placeholder. But that's not a polynomial. So in other words, no variables are in any denominator. So let's think. 5x to the 1 is the same as 5. 5x to the minus 1 is the same as 5 times 1 over x, which is 5x. So that is not allowed. So all exponents are in the set 1, 2, 3, 4. So I don't know why that's not in there. It's not, but I definitely need to make sure you're aware of that instead of assuming that you just know that. So a polynomial function in the variable x is simply a function where the rule for the input value x is given by a polynomial. So here's our function name p. P of x is equal to 3x squared minus 2x minus 5. Now if b is a real number, we denote the value of p of x on the input number b by p of b, and p of b is equal to 3 times b squared minus 2b minus 5. Now, I don't know what real number that actually gives us because b is an unknown, just like x is an unknown. For example, p of 5 is 3 times 5 squared minus 2 times 5 minus 5, which is 3 times 25 minus 10 minus 5, which is 75 minus 15, which is 60. Note that the value 5 is the input to the function p of x, and the output is the value of p of 5. So here's the thing. Every polynomial is a function. In other words, if I go back to my list here, to the very tip top, where I gave you those, oh, I don't have it anymore, do I? Because I started another one, started another page. Suppose I have 5x squared plus 2x minus 50. So that's a polynomial. I can simply declare it to be a function, and I will always know that its graph will pass the vertical line test. Polynomials are always functions, and that's kind of helpful too. So let's just go ahead and practice some more things. We're given the polynomial p of x is equal to 3x squared minus 2x minus 5. Notice the minuses here. They're inherent in the formula. So if x were itself minus, like it is over here, that minus 2 has to go along with the x. It can't co-opt the one that's existing. So let's find the value of p of 2. I guess p of 1 is what they want us to do. P of 1 is equal to 3 times 1 squared minus 2 times 1 minus 5, which is equal to 3 times 1 minus 2 times 1, which is 2, minus 5, which is equal to 3 minus 7, which is equal to minus 4. On the other hand, p of minus 2 is 3 times minus 2 is my base, and it's squared. Now the reason when I did 1 squared, I did that, but I could have just as easily did this, and maybe I should have. The reason I put the minus 2 in parentheses is that the minus 2 is the base. And the reason I'm talking about this is as I recall, on one of your last exams, I put a note in there that you needed to review a certain page in the e-text. And that's what deals with this little expression that I wrote here. If the base is negative and I'm raising it to an exponent, I need to enclose the entire base in parentheses to indicate that that's the base. So minus 2 squared is not the same as, in parentheses, minus 2 squared. So let's go on. I'm not going to deal with that any further. Minus 2, and x is minus 2, minus 5. So let's evaluate this. This is 3 minus 2 times minus 2 is 4. So that's 3 times 4. Minus 2 times minus 2 is plus 4. And then I have a minus 5. 3 times 4 is 12. Plus 4 minus 5 is the same as 12 minus 1, which is 11. So this is something you should be able to do in your sleep. Oh, so here we have a little bitty example of a polynomial in the variable t and a fun formula. So, finding the height of an object. The world's highest bridge, the Millau Viaduct Bridge in France, sorry, I don't know how to pronounce French words, is 1,125 feet above the River Tarn. Now, if we just ignore air resistance, the height of an object dropped from the top of this bridge is given by the function p of t is equal to minus 16t squared plus 125, where the input variable t is given in seconds. So if you're on the ground and you got a stopwatch and you see someone drop a basketball, and you know the original height of the building, or the the bridge in this case, and after 1 second you know how far it is above the ground, and after 2 seconds you'll know how far it is, etc. So we want to find the height of the object after 1 second and after 10 seconds. So P, I don't want to use that color, P of 1 is equal to minus 16 times 1 squared plus 1,125. Well, that's just minus 16 plus 1,125, and that's just equal to 1,109. And it says the height is given in feet. So that is 1,129 feet. So we can ask, how much did it drop in 1 second? In 1 second it drops 16 feet. So how far does it drop if we look at it 8 seconds after its drop? Well, that's minus 16 times 8 squared plus 1,125. Well, that's minus 16, and 8 squared is 64 plus 1,125. And this turns out to be minus 1,024 plus 1,125, and that turns out to be 101 feet. Now, of course, this is that little dot there meant feet, 101 feet. I should write it. Now, this is neglecting air resistance, but in real life, air resistance exists. So we would expect after 8 seconds for it not to have fallen quite 101 feet because air resistance slows it down. But you know, that's quite a bit. If you jump off a bridge and you fall 8 seconds, you're still not on the ground. 8-second fall. That's a lot. Here's an interesting question. You should guess that probably P of 9 is going to be less than 0. But of course, you only hit the ground and stop. You can't continue following. So we want to know for what value x do we have P of x equal to 0. And the x value that answers that, or in this case the t value, because it's a polynomial in the variable t, tells us the maximum amount of time, neglecting air resistance, that it would take. It would tell you the amount of time it would take for you to hit the ground. So here's a really easy part. So we've kind of been doing this already. To add two terms, we just collect like terms and add. And to subtract, we collect like terms and subtract. So the only difficulty here is subtraction, and I will show you what you need to do when there is a subtraction. So, and you'll always get it right. Students almost always get polynomial addition right. There's different ways to do polynomial addition. Actually, I will show you two different ways I think is included in our textbook and in these notes. So I'm going to add this polynomial to this polynomial, x cubed minus 10x plus 5. So like terms are determined by their degree. So I'm going to collect all of my x cubed terms first. And what I do is, when I'm doing this, I mark through them, otherwise I might skip one. And then I'm going to go to the degree 2 terms, and there's only one of those. Now the degree 1 terms, and the degree 0 terms. So that's what it means to collect like terms. Here's a grouping of degree 3 terms. Here's the grouping of the degree 2, the degree 1 terms, and the degree 0 terms. So you just look, and now you just add or subtract coefficients. So 11x cubed plus x cubed. So you have 11 of something, and you add one more of that something. You get 12 of that something. And what was that something? It was x cubes. Well, there's only one degree 2 term, which is a squared term. Now you have 1 of something and you subtract 10 of that something, so you're in the whole 9 of that something. So x 1 minus 10 is minus 9x, and minus 3 plus 5 is plus 2. So pretty easy. 12x squared, 12x cubed minus 12x squared minus 9x plus 2. And down here we have something that we've done. I placed them in parentheses. Before we do that, some of you may not be familiar with like terms. Like terms are terms which satisfy both criteria below. The first criteria is the terms have the same variables. In other words, if one term has the variable x and the other term has the variable y, they're not the same. They're not like. 2, each variable is raised to the same power. I guess I should add a word in here. Each like variable is raised to the same power. It's pretty simple, but we'll do it here because we're going to need it. We have 7x cubed y minus xy cubed plus 6x cubed y minus 4. So the two polynomials are actually grouped. When the groupings, in particular the second grouping or the first, if they're both, we don't write plus here. It's not written. It's understood. So when the symbol in front of the groupings is plus, we can go ahead and take those groupings off. And that's what I'm going to do. We won't be able to do that every time, but we're going to do it now. So since this is both we're adding in the signs, I erased the plus, but I'll put it back. All I'm doing is let me have a little bit bigger. Okay, that's supposed to be plus. Put it back. So what we have to do is collect like terms. So I always just start off with the first term, x cubed y. So what I'm looking for is a term with an x and a y where the x is cubed and the y is to the first power. So this has x and y, but the variables aren't raised to the same power, so that's not a like term. This one is, and the sign in front of it is plus. So I can mark out those two. Now my only other choice is to xy cubed and minus 4. So these two terms, if you need to at this point, you can underline groupings of like terms, and groupings that only have one term, then you can just write them down. So 7x cubed y plus 6x cubed y. 7 plus 6 is 13. X cubed y. And since there is nothing else included in that grouping there. There's only one xy squared term, and there's only one constant term. Then we're done. So take a second and see if you can do 8b. Now again, it's grouped in parentheses, but since there's pluses understood to be in front of the groupings, we can ignore that and we can just write the polynomials without the grouping symbols. The grouping symbols are parentheses. You won't be able to do that when we subtract, so keep that in mind. So these are polynomials in the variables a and b. So let's start adding them. 3a cubed. Is there another a cubed term? No, there's not. It doesn't matter which terms you go next. I'm just going to take them in the order that they go. There's a minus b. Is there any other degree 1b terms? There is, right there. It's a plus b. Plus 2a, and that's all of them. Plus 2a. Is there any other a terms? Yep. Right there is 1 plus a. And then I have a minus 5 and a plus 5. So here, if you want, you can group them. This is all by itself. This is a grouping of 2b terms. That's a grouping of 2a terms. And that's a grouping of 2 constant terms. So in the simplification step, the 3a cubed term is going to stay the same. Minus b plus b is 0b, so I'm not even going to bother to write down anything, because plus 0 is, you don't change anything. 0 is the additive identity. Plus 2a plus a. Well, if I have 2 of something and add another something to it, I get 3 of that something. And minus 5 plus 5 is 0, so I'm not going to write it. And here we have the answer. 3a cubed plus 3a. So I think on the next page we're going to learn how to subtract. And here I have a warning in a big, huge sign. Given a polynomial px, its opposite or additive inverse is denoted by minus px. And the px is completely enclosed in parentheses and is given by changing the sign of each of the terms found in px. This, for some odd reason, seems to be the hardest problem or technique for many intermediate algebra students. Many questions are missed because of this. And I actually tell you, failure to change the sign of each of the terms is the most common mistake in intermediate algebra. So let's just do a few of these. And it truly is the most common mistake. And let's see if we can avoid that by practicing quite a bit. So I'm going to be given px. That's going to be equal to 16x cubed minus 5x plus 7. Then minus px is found by taking px, and here's the point that you're going to want to be lazy about. Literally enclosing it in parentheses and put a negative sign in front of it. And once you've done that, we can apply the rule. Now, what I do is I look on the inside here, and I change each one of the signs. It's minus 16x squared plus 5x minus 7. Now you might be wondering why I added the parentheses and put the negative in front of it instead of just literally applying the rule right to my original. The reason being is many times you will be subtracting some terms, and one of those terms is going to have or B, a polynomial expression. So when you subtract it, if you're not ready to simplify it immediately and apply the rule, you need to enclose the entire thing in parentheses. There's another reason as well. This also connects it to distribution. This is the same as minus 1 times 16x squared. That's minus 16x squared. Minus 1 times minus 5x. That's plus 5x. Minus 1 times plus 7 is minus 7. So let's do this one, 10 and 11. So my px is 3x squared plus 4x minus 7. That's my px. And my qx is given by, what do? I put everything in parentheses first, and I've got it. So I don't need this minus px minus qx. So I want that space, so erase that down there. Should have written it above. So let's go. So this is, nothing's going to change. Sorry, I'm messing with the brush stroke width. Nothing's going to change here. But now I'm going to apply the minus polynomial rule and just literally look at the terms on the inside of the parentheses and change their sign. Minus 3x squared plus 2x plus 5. Literally, there couldn't be anything easier than looking at each of those terms and changing their signs. But you have to change the sign of every single term. And now we're going to go ahead and we're going to start the gathering and collecting of like terms. So I'm going to start with my 3x squared. It's a degree 2 term. Is there another 3x degree 2 term? There is. It's right there. Minus 3x squared. We'll go on to my degree 1 term, just because it was next in line. Is there another degree 1 term? Yes, there is. It's 2x. Now I'm ready for my degree 0 terms. If you need to remind yourself, there's a grouping of 2 like terms. There's a grouping of 2 like terms. There's a grouping of 2 like terms. 3x squared minus 3x squared is 0. That's 0, so I'm not going to bother to write it in my final answer. 4x plus 2x, if I have 4 of something and add 2 more of that something, I get 6 of that something. And minus 7 plus 5 is minus 2. So it's 6x minus 2. Now let's look at q of x minus p of x. And now we're going to go ahead and do it by literally writing down q of x and I'm going to apply the rule so I don't have to write things twice, minus p of x. So when I look at p of x, when I write it down, I'm going to change the sign of every term. So again, we're going to collect like terms. My degree 2 terms been written down. My degree 1 term and minus 5 plus 7. So 3x squared minus 3x squared, that's still 0. Minus 2x minus 4x is minus 6x. And minus 5 plus 7 is plus 2. So I get minus 6x plus 2, and before I got 6x minus 2. So this is qx minus px, and this is px minus qx. And you'll notice that these two are almost exactly the same, except each term has the sign changed. And that's exactly true in math. 7 minus 3 is the same thing as minus 3 minus 7. So 4 is equal to minus 4. So we see that right there. To subtract here is really important, because you're going to see this in applied problems. They'll be coming up sometime. I don't think in today's lecture. To subtract A from B, you're taking away from it, means what are you taking A away from? B. So it translates to B minus A. So we're going to subtract, this is another common error, that's the reason I put this note there, subtract this polynomial from this polynomial. So again, we're going to go ahead and we're kind of feeling a little bit cocky here. We think we can do it without writing parentheses. So I'm subtracting this polynomial from this polynomial. So the second polynomial, 10x cubed y squared minus 7x squared y, will be the thing that we're subtracting from. And I'm subtracting this from it. So I'm going to change the value of each sign. Of each term. Change the sign of each term. There, it came out right. So again, let's gather like terms. I just start from the left and move to the right. So I've got that down. Do I have any x cubed y squared terms? Yep, there's an x cubed y squared term. So they're like. Do I have any others? Nope, that's all of those. Now I'm going to go right ahead and do minus 7x squared y. Do I have any other x squared y terms? I don't. I have an x squared y squared term. Do I have any other x squared y squared terms? I don't. Minus 2y. So all of this, you know, marking through up here, that's just bookkeeping, and it helps. So my only two like terms are these. These are all individual like terms. There's only one of them. So there's not much to do here at the very end. 10x cubed y squared minus 4x cubed y squared is 6x cubed y squared. And that's going to be, did I write everything down right? 4x cubed y squared minus 3x squared y squared minus 2y squared. 10x cubed y squared minus, oh, sorry. That's supposed to have a 2 on it. So let's correct that right there. So these are two like terms. Yeah, that's another copy error. That's really annoying. And when I'm grading your what you write, I try to check if there's a copy error. Of course, you have to be careful. If you've got time, you can check it. But many times on a timed exam, you don't. And it's annoying when you know what you're doing, but you miss a question because of a copy error, just like that. And I try to be very, very lenient on those. So, minus 2y squared. Notice I miscopied it all the way down to there too. Two copy errors in one. I mean, I can say I have an excuse of talking and writing at the same time. But no, I had problems with that. I mean, in grad school too, especially, you don't do an awful lot of this stuff in grad school on an exam. We do proofs and things like that. But I mean, it's something that I am at least sensitive to. Some people suffer from it more than others. So, just like any function, it has a graph. So now we're going to recognize graphs of polynomial functions from their degree. So remember, always y is equal to f of x. And f of x is going to be a polynomial function, and hence it will have a degree. So we have some information to help you just recognize a graph by its degree. So if the degree of the polynomial is degree 2, and the coefficient of the degree 2 term is positive, then the graph will look, well, it's called a parabola opening up. If the coefficient of the degree 2 term, of the x squared term, is negative, it will be a parabola opening down. So I'll give you two examples of that really fast. So we will go minus 3x squared plus 5. There you see it opening down. And over here, we'll do 10x not cubed, but squared minus 10. Maybe I shouldn't have done it minus 10. I'll just put it minus 0. And there it's opening up. So degree 3 polynomials. The coefficient of x cubed, notice, it's kind of like you have half of a parabola, but instead of going up in the positive direction, you keep the same form, but you start going down. So the degree 3 terms, so if the coefficient of x cubed is positive, then it exits the graph in the first quadrant and the third quadrant. If the coefficient is negative, the ends of the graph exit in the second and the third quadrant. So let's look at two examples of that. X cubed plus 2. So again, it's exiting in the first and the third quadrant because the coefficient on the degree 3 term is positive. Now we'll do minus 2x cubed plus 4. And here we see it exiting in the second and the fourth. So this is always nice. It's always nice to have a visual question. Determine which of the following graph could most closely resemble a degree 3 polynomial. So since it's a degree 3, we can immediately eliminate A and C because those are degree 2 graphs. So the first thing you do is you notice it's a degree 3 polynomial. So you know it's going to look like these three types. Its leading coefficient is positive. So that means it's going to exit in the first and the third quadrant. So the answer is B. And okay, that's it for today. We've finished the end of section 5.3.